Okay, now this next chapter on gravitation, this will be our last chapter we're going to cover. I know in the syllabus we were going to go up to 13, but because of the coronavirus and everything else, we're going to stop at chapter 12. And we don't need to do the very last two problems in assignment 12. You can just go up to 10, 1 through 10 right here. Chapter 12 covers gravitation. And you might say, well, we've already done gravity. We said the force of gravity was mg, and we also said the potential due to gravity was mgh, and when we took the derivative of that, it gave us this right here. Okay. But I should say that Newton never said this. This wasn't exactly the truth right here. You couldn't handle the truth before. Now I think you can handle it a little bit better. What Newton did say is said, if we have 2-point masses, two-point masses right here, they are attracted to each other with equal and opposite forces. They have to, Newton's third law right here. And he said the magnitude of that force is proportional to the product of the two masses divided by the separation of them squared right here. Now, you'll notice that out of all the forces we've had so far, this one was a little different than the others. You know, we had things like normal forces pushing against the wall right here. You have to actually touch the wall right here. When you have a rope, you have to actually tie the rope to the object right here. But this is the first force that we've had that was action at a distance. The Earth pulls this thing down, but the Earth isn't even touching it. There's nothing in between right here. So we call this an action at a distance. Well, how does this pen know that the Earth is there? Well, the Earth must send off some information, just like this should send off some information that there is a pen here. And it's going to send it off just like a light bulb sends off information that there's a bulb there because the light comes out right here. Light comes out in all different directions right here for this bulb right here. And so we can see that if we looked at the total amount of light coming here, it's got to be the same amount going there at some later time. It's not going to grow. But you'll notice that the area is getting bigger here as opposed to there. If the area gets bigger, the intensity must drop by the same factor. Well, we know that the area of a sphere goes as r squared. It's actually 4 pi r squared, but it goes as r squared. So the intensity must drop by 1 over r squared because it's thinning out as it grows right here. Matter of fact, anything that emanates out in 3 dimensions must decrease by a 1 over r squared factor. So if this were a radioactive source and you could put a Geiger counter right there, if you doubled the distance, the clicking rate would be 1/4 the rate right there. Anything that emanates out in 3 dimensions is going to be 1 over r squared. If it only emanated out in 2 dimensions, well, what would emanate out in 2? Let's say let's say this is a pond, this is a level of water on a lake, and you drop a pebble into it, and the waves go out. Well, the waves only go out along the surface. And there, you don't look at the area, you look at the length. And the length is 2 pi r, so when you get out to here, it's only a function of r, so the intensity would just drop off as a 1 over r. So if we lived in a 2-dimensional universe where we have to walk right along the surface, and if you came to someone, you couldn't go around them, you'd have to climb over them, or have them climb over you, gravity would just be a 1 over r. If we lived in a line right here, so all you could do is push the person in front, you couldn't go around him or under him or side him, then there wouldn't be any r right there. It would just be a product of the 2 masses. If we lived in 4 dimensions of space, that means there'd be more ways of getting around than this and this. Don't ask me what they are, but there would be more ways. It would be an r cubed right here. So this kind of tells us about the dimensionality of the space right here. Well, Now, since this is just proportional, we need to get a proportionality constant in there, right there, because this, first of all, the units don't work out. This is newtons and this is kilograms squared over meters squared. And the way we define the kilogram and the way we define the meter and stuff dictates what this constant is. And this G, so this, we're going to use this constant that makes all this, cleans up the units and puts the strength right. We're going to call it big G right there, not little g, big G. And Newton couldn't measure it. They couldn't measure this until 200 years after Newton came up with this. And they measured it to be 6.6 times 10 to the minus 11. Very small number right here. And the units, I need newtons, but I want to get rid of the I want to get rid of the kilogram squared and the meter squared, so it's a Newton meter squared per kilogram squared. Now, Newton didn't know this, what this value was, but he guessed it. He guessed 6.5 times 10 to the minus 11, so he was a very good guesser. Now, you'll notice this is a very weak force, because if this is 1 kilogram, and this is 1 kilogram, and you separate it by 1 meter, these 2 kilograms, then 1 times 1 over 1 squared is 1. 1 times this number is very small. It's this number. That's like a trillionth of a Newton. You wouldn't be able to notice that. Maybe out in space, if you watched it long enough, it would eventually come together right here. But this is a very weak force right here. Matter of fact, when you get into 4B next semester, the electrical forces are so big compared to this force that you'll just ignore gravity right there. It's comparing this to the electrical force is like comparing the Earth to a grain of sand. You don't care about 1 grain of sand when you're talking about the Earth. Well, we're not dealing with point masses, we're dealing with planets and spheres and stuff. So let's say we have a point and a sphere right here. Well, the sphere is made up of a bunch of points, so you'd have to add up all these forces. There's an infinite number of them. When you do all that, it's just what the answer is, it just comes out to be exactly the same equation, but for your m, you're going to put the total mass, and your r, you're going to put from here to the center. It's only from center to center. This only works for a sphere. It wouldn't work for a cube or a stick or any other shape. It only works for spheres right here. And so now, if we had 2 spheres, let's say we have a sphere and we have another sphere, maybe the moon and the earth. That means for every point here, you'd have an infinite number of them. So you'd have an infinite number of an infinite number. When you work all that out, again, it's the same equation as long as they're spheres, where the r is from the center of one sphere to the center of the other sphere, right here. So again, it only works for spheres, right here. Now, what about us? Are we a sphere or a point? Well, some people are points, some people are spheres, right here. We'll assume we're points relative to the Earth, right here. So now, if we're just standing here on the Earth, right here, and we ask what is the force between us and the Earth, right here, we get G times the mass of the Earth, m over the distance from here to center, which is just the radius of the Earth. You notice the only time we're ever going to notice this force, since G is such a small number, I need m, one of these m's to be huge, to make this cancel out the G right here. And where am I going to find a mass big enough? The Earth right there. Matter of fact, don't we call that force our weight right here? This is just our weight. It's the force that the Earth pulls down on us right here. It's G, mass of the Earth, m over the radius of the Earth squared. And you notice these, when you're walking around the Earth, these guys don't change much. Well, the radius of the Earth might change a little bit when you go up to the mountains, but compared to the size of the Earth, you don't even notice it. So all of this is pretty much constant. And if you plug in the number, we just call it, that would be about 9.8 meters per second. That's what we called the G before. This is what we were doing before. We weren't leaving the Earth very far. We were just, matter of fact, for this force to change by just 1% of this, you have to go up 100,000 feet. And so none of our projectiles we threw it up 100,000 feet. So that's why we can just call G all the time right here. But if you want to get real accurate, if you're throwing projectiles more than 100,000 feet up, you probably want to use this force rather than that force right there. If you wanted to find out what G as the moon was, you would put in G, mass of the moon, over the radius of the moon squared, or whatever planet you wanted right here. Since this is an inverse square law, if you got on a ladder that was equal to another radius right here, so the radius of the Earth is 4,000 miles, so if you got on a ladder that's 4,000 miles out here, if you double the radius, the force gets 1/4 as much, because we call that an inverse square law. If you triple the radius, triple down here, it'd be 1/9 of your weight right now, way out there, triple. So this is going off as a 1/r². It never goes to 0, but it drops pretty darn fast. I know people say where the planets are when you're born affects your astrology or whatever, but the amount of force, if you calculate it, is so small where Mars is when you're born. Just where a person standing in the room is much bigger effect right there. So, okay, so now there is G at the surface. It just drops off when you go up. Now what happens if you go into the Earth right here? Well, before I dig a hole and you weigh yourself into the Earth, you would think at the center of the Earth you would weigh a lot, because R would go to 0, and if they go to, when the denominator goes to 0, your calculator starts smoking right here, and you'd hate to calculate your weight and find out the calculator smokes. So we'd like to know, how much would you weigh right there at the center? Well, let me just assume we have a hollow Earth right here. Suppose there's a hollow, a shell, and someone places you at some location inside, not at the center, just off some spot right there, hollow spherical shell. And you calculate which way you pushed right here. Well, you'd think you'd be pulled over to this side because you're a lot closer, but there's a lot more mass on this side. And it just so happens, because of the shape of a sphere, that the forces all cancel out right here. And matter of fact, the only matter that matters, that's pretty profound, is the mass within your radius. So when you come over here and you put in that mass, it's really the mass within your radius. Well, when you're on the surface of the Earth, all the mass is within your radius. When you're right here, there is no mass within your radius, so you would just sit there and float right there. It wouldn't work for a cube, but it works for a sphere. This is kind of profound. The only matter that matters is the mass within your radius. We'll find that a lot about this in 4B right here when you do the electrical forces, because a lot of this is going to be very similar to what you do in 4B. So really, we could just say it's the force is G, M, mass inside your radius, times your M over R², right there. Now, you notice right here, you would just float, but what if someone landed on a rocket ship? Then you'd break the symmetry, and they would float over. They'd have to greet you, whether they liked you or not. They have to. Or if this was some sort of a monster creature right here, and you land on this ship, no matter where you move, he's going to follow you, and he'll be able to get you no matter where you go. And so maybe it'd be a good scary movie. But then so then you'd have to land what? 2 rockets simultaneously on opposite sides so you can kill it right here. We always wonder who's the monster when we usually kill their creatures right there. They were living peacefully right there. Okay, so now if you go into the Earth, the mass within your radius is getting smaller, and the radius is getting smaller. They're both getting smaller right here, and when you get to the center, they're both 0 right here. Well, what's 0 over 0? Well, it depends. It depends on which one is going to 0 faster. If the denominator goes to 0 faster than the numerator, then this goes to infinity. If the numerator goes to 0 faster than the denominator, if the numerator goes to 0 faster than it's 0. If they both go to 0 at about the same rate, then it could be anywhere between 0 and infinity. So that's why they call it undefined in math right there. But in our case, The mass goes as the volume when you go inside it, and that's going to go as the radius cubed. And the radius cubed goes faster than the radius squared, so this would go to 0. And matter of fact, if you were right there at the center of the Earth, you would weigh nothing. Well, you can't weigh anything, because if you were right there at the center of the Earth, you couldn't, there is no below you to stand on the scale. Everywhere is above you right here. You'd just be floating right there. So your weight goes to 0 right there, linear right back down to 0 for a uniform density Earth right there. So you can see that where you weigh the most is right there at the surface of the Earth. So if you want to lose weight, climb a mountain, dig a hole, one or the other. Just don't weigh yourself at sea level right there. Okay, so now that we have this force right here, suppose we just have 3-point masses. I put them on an equilateral triangle just to make life simple. And they're not moving, which means you're holding them down. So we're holding them down with our hand. I don't care about the hand force. Or we nail them down or something. And we just want to find what is the gravitational force on this guy due to these two. Well, this guy is attracted to that one, and this one is attracted to that one right there. And since their lengths are the same and their masses are the same, their forces are the same. That force is this, and that force is the same right here. So if we wanted to get the total force, it might be easier to put my coordinate system like this, because then all the forces this way cancel, and all we get is double one of these in that direction right here. And so that would just be, this component of force would be 2F cosine 30. We know what the cosine 30 is, we know what the F is. Cosine 30 is the square root of 3 over 2. The 2's drop out and you get the square root of 3 times that. So there is the total gravitational force due to these two right there. Now this wouldn't be stable, they'd all want to come together, but later I think you have a problem in the book where you have these things orbiting each other, and that's holding them out right there. So, okay. Well, let's look at orbital. Let's say we have the Earth and we have something orbiting the Earth right here. Well, if you have something orbiting the Earth, the only force we have is the inward force of gravity, which is that right there, where r is the distance from center to center. And since we're going in a circle, we can set it equal to mv squared over r. Matter of fact, every homework problem you see on this chapter where you see something going in a circle, that would be my first step. Take the sum of the forces, set it equal to mv squared over r. Cancel the little m, solve for the v. There's the speed. We call that the orbital speed right here. There's how fast you have to go so you don't fall back into Earth. If you're going slower than that, you'll spiral in. If you're going faster than that, you'll spiral out right here. So this thing right here, you can see if you wanted to get like the orbital speed of the space station, you just put in how far out the space station is. It's pretty much 4,000 miles, maybe. It's just a little bit above the surface of the Earth, and that orbital speed is about 17,000 miles an hour. If you want to know how fast the moon's going, put the r from the Earth to the moon. That would tell you how fast the moon's going. If you want to know how fast anything is going around the Earth, just plug in right there, as long as it's going in a circle. And now, we already said, since it's going at a nice constant speed in a circular orbit, we can say, just from chapter 3, the speed is the distance over the time. So now we can get the time it takes to orbit right here. The time, I just solved for the time, plug it in your speed. So there's the orbital period. If you plug in for the space station right here, you can plug in that. You get about 90 minutes. So it goes around the Earth every 90 minutes. If you plug in the distance all the way out to the moon, you'll get about a month to go around. It takes like a month for the moon to go around. So this is the time for anything to go around the Earth. If we wanted to find the time it takes to go around the sun, we would just put in the mass of the sun right there. You just change the mass right there. Now, here I assume that this mass was insignificant compared to that mass. But what if you have two equal masses right here? Call that a binary system. Most stars are binary system, but I'm going to make them two equal stars. They orbit their common center of mass. There's the center of mass right there, so they're just going around like this. Now, again, you got something going in a circle. So you take the sum of the forces. We'll just look at the force on this one. But what do we put in here for the distance between here and here? That's 2r. But over on this side, this is just mv squared over r. This is the radius of the circle you're in, that r. This is the distance between the two, right there. Okay, and so now from this, we can do the same thing. We can solve for the v, get rid of an r, and get rid of an m. And then we could get the period right there by doing the same thing right there. It just gives me a 4 up there. So, you know, if there was a binary star system out there, and you could measure the period. How do you measure the period? Maybe your eye is looking this way, and if the stars go in front of each other, they block each other, and you get a little dip in light, they can get the period right there, because the light gets dimmed every time one passes in front of the other, so you can get the period. And if they could get the separation, then they could get the mass of the two if they're equal masses right here. So, so this is for a binary system. So just remember in the homework, anytime you see something going in a circle, first thing you should think of is sum of the forces equals mv squared over r. Matter of fact, not just in this chapter, it's in the whole life right there. Okay. So there's the first part of gravitation. This with the F equals mg. Next one we'll hit with the energy right there.